Hi, and welcome to my talk titled Misperception of the Distance of Virtual Augmentations. Today I'll be discussing how depth perception is impacted by Q conflicts in augmented reality, focusing on depth cues like occlusion and binocular disparity. Then we'll go through two experiments. The first examines depth matching in AR under Q conflict, comparing within and outside reach space. The second extends this by incorporating visually guided reaching. Finally, I'll summarize key findings and their implications for AR depth perception. This is an example of a real-world scene, and many modern AR displays are capable of spatially mapping the 3D layout of such scenes. What this allows us to do is correctly place virtual objects in that mapped space, such as this cube. And this is important for rendering virtual content within that space because now we can simulate things like collision detection, as well as occlusion, where the table properly obscures the virtual cube when it's placed underneath. However, if a user moves into a new environment or new objects are introduced into the scene, such as this mug, sometimes those new things are not updated in the mapping. Therefore, virtual objects may not always be correctly rendered. In this example, the cube's position moves from in front of the mug to behind it. But because the mug is not spatially mapped, you can see that from the observer's point of view on the bottom right, even though it's behind the mug, it's still superimposed on it. There are two important depth cues relevant to this type of viewing scenario. The first is binocular disparity, which is the difference in the position of an image on the retinas of both eyes. This provides metric depth information signaling how far away something is. And this is a stereo pair, as an example, arranged for cross fusion. If you can free fuse this, the disparity in the image shows that the cube on the right should be seen as closer compared to that of the left. There are also many monocular depth cues, such as occlusion, that provide depth order only. In this example here, the blue cube is occluding part of the red, which means that the blue should be perceived as closer. And there's evidence showing that occlusion can influence both the direction and the accuracy of perceived depth from stereopsis. So under natural viewing, disparity and occlusion are both correct. In this example here, the red block properly occludes part of the green ball. However, as I showed at the beginning of the presentation, in AR you can have a situation like this, where a virtual ball's distance is behind the red block, but it's still superimposed on it. Here, binocular disparity tells us that the ball is behind the block, but occlusion tells us that it is in front, resulting in a depth cue conflict. Currently, it's unclear how conflicting occlusion and binocular disparity cues affect the accuracy of perceived depth and whether any impacts are modulated by viewing distance. So here, we assess how these cue conflicts in AR impact depth localization under both within and outside reach space distances, as well as a visually guided reaching task. In experiment 1, observers performed a depth matching task outside and within reach space distances. All stimuli consisted of virtual letter A's that were presented at one of 7 distances within each respective condition. A physical surface was placed on the table which acted as the occluding surface. This meant that any letter positions in front of the surface did not have a cue conflict because they would not be occluded, while letter positions beyond the surface did have a cue conflict because they were still visible when they should be occluded. Additionally, we also tested a no conflict condition where the surface was removed entirely. The participant's task was to match the distance of a probe to the perceived distance of the letter. So the letter was presented for 1 second, and then it disappeared, and then a virtual probe's distance was adjusted using a gamepad to match the remembered distance of the letter. Before showing the results, I'm just going to describe how things will be presented. Each plot represents the reach space conditions, and the match distance is plotted as a function of the actual letter's distance, and the dashed black line depicts perfect performance. So first I'll show the no surface results. Although there was a slight underestimate, observers performed very accurately and the results scaled linearly with theoretical distance. And when we introduce the surface, you can see that observers do very well up until the point of the surface. Then they progressively underestimate the distance in both conditions. In experiment 1, observers showed decreasing matching accuracy of the letter's distance when positioned beyond the surface, in other words, when there was an occlusion conflict, indicating that they are unable to ignore conflicting disparity and occlusion cues. There's also strong evidence showing distinct neural pathways in the human visual system, also known as the two pathways hypothesis. According to this hypothesis, the visual system's ventral stream governs perception and is prone to visual distortions such as cue conflicts, while the dorsal stream processes visual information for action and is more resistant to these types of distortions. So if perception and action are truly dissociated, the underestimations observed in experiment 1's visual task may not occur in a more interactive context. Therefore, in a second experiment, we explore the impact of conflicting occlusion and binocular disparity through a visually guided reaching task. The task was very similar to that of experiment 1, where the letter is presented for 1 second and then it disappears, but now the observer reaches and points with their fingertip to the remembered position of the letter. So like experiment 1, I'm plotting the match distance as a function of the true distance with the black line showing perfect performance. As expected, observers performed very accurately with a slight overestimate in the surface absent condition. However, when the surface was present, observers still showed the same pattern of progressive underestimation as experiment 1. To conclude, in this study we demonstrated the strong and robust impact of incorrect occlusion on perceived depth in AR, regardless of the viewing distance and whether interaction was involved. When depth cues are properly presented, observers reliably perceive the correct depth of virtual objects. However, incorrect occlusion information biased the perceived depth of virtual objects significantly closer than their actual position. So this bias, where perceived depth is pulled in the direction of the occluder, highlights the need for accurate occlusion rendering in AR, which means that AR applications requiring accurate depth interaction must avoid incorrect occlusion arrangements. So with that, I want to thank my collaborators and thank you for your attention.